And now in this lecture we'll answer two questions. In the first question we'll find out the size of this angle AMQ that is equals to x. We have to find out the value of angle x. And in the second question we'll find out the area of this circle that is inscribed by this trapezoid ABCD. So we start with the first question. In the drawing we have a semicircle. Point O is the center of this semicircle. AB is the diameter of this semicircle. In addition, we know that OS equals to SB. And inside this semicircle, we have this square PQSO. Again, our task is to find out the size of angle AMQ is equals to x. We have to find out the value of angle x. So first of all, we know that all the angles inside the square are right angles. So those four angles are all right angles. So this is a right angle. This is also a right angle. And this is a right angle. Likewise, all the sides of any square are equal to each other. That is to say, side QS equals to side OS. QS equals to OS. So we can write here that QS equals to OS. And it is given as a question that OS equals to SB. So OS equals to SB according to what is given as the question. So from this equation, QS equals to OS equals to SB, we derive that QS equals to SB. QS equals to SB. Those two sides are equal to each other. In the next step, we'll do a construction. That is to say, we'll join points B and Q together by a straight line. By joining points Q and B, we created the right triangle QSB. In the right triangle QSB, those two sides are equal to each other. But before that, we know that AB is the diameter of this semicircle. So AB is the diameter of the semicircle. It is absolutely a straight line. So if we focus on the upper side of the straight line AB at point S, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line AB at point S? We have this angle that is right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the right triangle QSB, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes, according to the rule that in front of equal sides in a triangle there are equal angles. So those two angles that are located in front of those two equal sides must be also equal to each other in their sizes. So if we define the size of this angle as y, then the size of this angle must be also equal to y because they are equal to each other. We know that the sum of the angles in any triangle is equal to 180 degrees. So what is the sum of the angles in this right triangle QSB? In the right triangle QSB, Which I guess we have in the right triangle QSB, we have y plus 90 degrees. In total, they must be equal to 180 degrees. According to the rule, that the sum of the angles in any triangle is equal to 180 degrees. So 2y plus 90 degrees, in total it must be equal to 180 degrees. The triangle QSB, the sum of the angles must be equal to 180 degrees. That is to say, 2y plus 90 degrees must be equal to 180 degrees. Here we subtract 90 degrees from this equation, and we get that 2y equals to 180 degrees minus 90 degrees is 90 degrees. So 2y equals to 90 degrees. Here we divide this equation by 2, and we get that the missing angle y equals to 90 degrees over 2 is 45 degrees. So the missing angle y equals to 45 degrees in its size. So this is the missing angle y, that equals to 45 degrees in its size. This is also angle y, that equals to 45 degrees in its size. We joined points B and Q together by a straight line, and then we extended the straight line QB by straight line until it touches the circle. We define the touching point of the extended line QB with this circle. This point is point N. When you extend a straight line by straight line, the result must be a straight line. So BN must be a straight line. If you focus on the left side of the straight line BN at this point, point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the left side of the straight line BN at point Q? We have this angle that is equal to 45 degrees, plus this angle that is a right angle, plus this missing angle that is actually angle NQP. So that the sum of those three angles must be equal to 180 degrees according to rule 3. And again, the sum of the angles the left side of the straight line in bit point Q must be equal to 180 degrees. That is to say, 45 degrees plus 90 degrees plus the size of the missing angle in QP, in total must be equal to 180 degrees according to rule 3. 45 degrees plus 90 degrees is 135 degrees, so 135 degrees plus the missing angle NQP, in total they must be equal to 180 degrees. So here we subtract 135 degrees from this equation and get the missing angle QP is equal to 185 degrees minus 135 degrees is 45 degrees. So the missing angle QP equals to 45 degrees in its size. This is the missing angle NQP, is equals to 45 degrees. In the next step, we will join points M and N together by a straight line. And we will join points N and N together by a straight line. By joining points N and A, we created triangle A and B, but we also created triangle A and B. Triangle A and B subtend on AB. AB is the diameter of this semicircle. And according to rule 7, any peripheral angle that subtend on the diameter of the semicircle or a circle must be equal to 90 degrees in its size. So, repeat quickly rule 7. According to rule 7, if a peripheral angle subtend on the diameter of the circle, then it is equal to 90 degrees in its size. In the drawing, we have a circle. This is peripheral angle ACB. Peripheral angle ACB subtend on chord AB. That is the diameter of this semicircle. Therefore, according to this rule 7, peripheral angle ACB must be equal to 90 degrees in its size. We can implement rule 7 in our drawing. Why? Because in our drawing, we have, this is peripheral angle A and B, that subtend on AB, that is the diameter of this semicircle, and therefore peripheral angle A and B, peripheral angle A and B, according to rule 7, must be equal to 90 degrees in its size. So in the right triangle A and B, 45 degrees plus 90 degrees, plus this missing angle, in total they must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Therefore, this first missing angle must be equal to 45 degrees in its size. So, in the right triangle A and B, in front of those two equal angles, we have those two sides that must be also equal to each other on their lengths, according to the rule that in front of equal angles in the triangle there are equal sides. So those two sides are equal to each other. So side AN is equal to side NB. So therefore, triangle A and B is also an isosceles triangle. Triangle A and B is an isosceles triangle because side AN equals to side NB. So triangle A and B is simultaneously an isosceles triangle and also a right triangle. So now we should find out that the right triangle A and B is also an isosceles triangle. The right triangle A and B is an isosceles triangle. And the base of this isosceles triangle, triangle A and B, is AB. AB is the base of the isosceles triangle, triangle A and B. But AB is also the diameter of the semicircle. So if the radius of this semicircle is r, then the diameter must be equal to 2r. So we can write down that AB is the base of the right triangle, of the right and isosceles triangle, triangle A and B, and AB is also the diameter of this semicircle, that is equals to 2r. AB is simultaneously the base of the isosceles triangle, triangle A and B, and AB is also the diameter of this semicircle, that is equals to 2r. So here we can implement rule 24 in our drawing, or in the right and isosceles triangle, triangle A and B. So I repeat quickly on rule 24. According to rule 24, the perpendicular to the base of an isosceles triangle bisect the base. In the drawing, we have the isosceles triangle, triangle ABC. Triangle ABC is an isosceles triangle because side AB equals to side AC. from point A, we go perpendicular to the base BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BC. This point is point O. And according to this rule 24, the perpendicular AO to the base BC bisects the base BC. That is to say, divides the base BC into two halves. Each half, of course, equals to BC over 2. So the first half is BO, that is equals to BC over 2. And the second half is OC, that is also equals to BC over 2. And of course, BO equals to OC. So we can implement rule 24 in our drawing. Well, because in our drawing, we have the associated triangle, triangle A and B. AB is the base of the associated triangle, triangle A and B. So the perpendicular N to the base AB bisects the base AB. That is to say, divides the base AB into two halves. Each half equals to AB over 2. But AB over 2 is 2R over 2 because AB equals to 2R. AB is the diameter of the semicircle, that equals to 2R. So AB over 2 equals to 2R over 2, and 2R over 2 is R. So each half of the base AB, each half must be equal to R, that is the radius of the semicircle. So the first half equals to R, and the second half also equals to R. But the question is where the perpendicular to the base AB will touch the base AB. The perpendicular to the base bisects the base. That is to say, it divides the base into two halves. Therefore, the perpendicular from point N will touch AB at the midpoint of the base AB. Again, the perpendicular from point N will touch the base AB at the midpoint of the base AB. What is the midpoint of the base AB? AB is also the diameter. And note that the midpoint of any diameter is at the center of the semicircle or the center of the circle. So the midpoint of the diameter AB is at point O, that is the center of the semicircle. Again, the midpoint of the diameter AB is at point O, that is the center of the semicircle. Therefore, the perpendicular from point N will touch AB at point O, that is the center of the semicircle. So it is perpendicular NO, that is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. So the perpendicular NO bisects the base AB. Each half equals to R. The first half AO equals to R, and the second half AO also equals to R, that is the radius of this semicircle. We know that the opposite sides of a square are parallel to each other. So in square PQSO, side PQ is parallel to the opposite side OS. So those two angles are defined as corresponding angles, and are located between the parallel lines PQ and OS. Therefore, they must be equal to each other in their sizes. But this angle equals to 90 degrees, and therefore this angle must be also equal to 90 degrees in its size, according to the rule that corresponding angles between parallel lines are equal to each other. This is angle ABN. Angle ABN equals to 45 degrees in its size, and it's subtend on chord NA. Again, angle ABN equals to 45 degrees in its size, and it's subtend on chord AN. Likewise, this is angle AMN. Angle AMN subtend on the same chord called AN. Again, peripheral angle AMN also subtend on the same chord called AN. And because of the fact that those two peripheral angles subtend on the same chord called AN, they must be equal to each other in their sizes according to rule 16. So repeat quickly on rule 16. according to rule 16, peripheral angles that subtend on the same chord are equal to each other. In the drawing we have a circle. This is peripheral angle AOB that subtend on chord AB. Likewise, this is peripheral angle ACB. It is also subtend on the same chord called AB. And because of the fact that those two peripheral angles subtend on the same chord called AB, they must be equal to each other in their sizes. That is to say, peripheral angle AOB equals to peripheral angle ACB, or alpha equals to beta. So we can implement rule 16 in our drawing. Because in our drawing, those two peripheral angles subtend on the same chord called AN, and therefore they must be equal to each other in their sizes. But the size of this peripheral angle ABN is 45 degrees, and therefore the size of this peripheral angle AMN must also be equal to 45 degrees in its size, because it subtends on the same chord called AN. So peripheral angle AMN equals to 45 degrees in its size, according to rule 16. In the next step, I'll prove that quadrilateral NMQP, this is quadrilateral NMQP, I'll prove that quadrilateral NMQP is a cyclic quadrilateral. That is to say, it can be inscribed by a circle. Again, I'll prove that quadrilateral NMQP is a cyclic quadrilateral, that is to say, it can be inscribed by a circle. So, what is the meaning of the sentence that a quadrilateral can be inscribed by a circle? Actually, this is quadrilateral ABCD. The red quadrilateral is quadrilateral ABCD. Quadrilateral ABCD is inscribed by this circle. Why quadrilateral ABCD is inscribed by this circle? Because of the fact that all of its four vertices, that is to say A, B, C, and D, lie on the circle. So a quadrilateral is inscribed by a circle only if all of its four vertices lie on the circle, like this quadrilateral ABCD, that all of its four vertices A, B, C, and D lie on this circle. So we have to prove that all the four vertices A, N, Q, and P lie on a circle that inscribed this quadrilateral NMQP. So, actually, before that we have those two angles. This is the angle NMP, this equals to 45 degrees in size, and it's subtend on the base NP. Likewise, this is angle NQP, that is also equals to 45 degrees in size, and it's subtend on the same base NP. And because of the fact that those two angles are equal to each other, each of them equals to 45 degrees, and they are both subset on the same base NP, they fit to be inscribed by circle. They fit to be inscribed by circle because of the fact that those two angles, they are both equal to 45 degrees, therefore they are equal to each other, and they are both subtend on the same base NP. Actually, it is according to rule 16 that if you have two peripheral angles that subtend on the same chord, they are equal to each other. That is to say, if we inscribe those two angles in a circle, then we get that those two peripheral angles subtend on the same chord called NP, and they are equal to each other. They are equal to each other, each of them equals to 45 degrees, and therefore they are equal to each other. Here we have those two peripheral angles, peripheral angle PMN and peripheral angle NQP. They are both subtend on the same chord called NP, and therefore they are equal to each other. Each of them equals to 45 degrees, and therefore they are equal to each other. Therefore, those two angles that subtend on the same base NP, they are fit to be inscribed by a circle, according to rule 16. So we have to prove that quadrilateral NMQP is inscribed by a circle. Can be inscribed by a circle, that is to say it is a cyclic quadrilateral. So first of all, I'll copy this triangle NQP. This is also angle NQP. In triangle NQP, we have angle NQP. This is equal to 45 degrees in size, and it's subtend on the base NP. So actually, this is triangle NQP. This is triangle NQP that I copied from the original domain, and this is angle NQP. This is equal to 45 degrees in its size, and it is subtend on the base NP. Again, angle NQP equals to 45 degrees in size, and it's subtend on the base NP. And we have the rule that says that all the triangles in the world can be inscribed by circle. Again, all the triangles in the world can be inscribed by circle. For that reason, we can inscribe this triangle QNP by this circle. Okay? So we inscribe this triangle NQP by this circle. Okay? And then we have those two angles. This is angle NPQ, that's equals to 45 degrees in size, and subtend on chord NP. Likewise, this is angle NP, peripheral angle NMP, that is equals to 45 degrees in its size, and is subtend on the same chord called NP. And all the angles that are located outside this circle and subtend on the same chord called NP will be less than 45 degrees. For example, this is angle NLP that is definitely located outside this circle, and it is inscribed on chord, it is subtend on chord NP. And the size of angle NLP is 49 degrees, that is less than 45 degrees. Likewise, this is angle NOP that is subtend on chord NP. The size of angle NOP is 85 degrees. So all the angles that inside this circle and subtend on chord NP will be greater than 45 degrees, while all the circles, all the angles that subtend on chord NP and located outside this circle will be less than 45 degrees. This is angle NLP that is outside this circle, and the size of angle NLP that subtend on chord NP is 39 degrees. Therefore, we can say that only the angles that are located on the circle itself and subtend on chord NP will be equal to 45 degrees in their sizes. All the other angles, for example, all the angles that are located outside this circle and subtend on chord NP will be less than 45 degrees. Likewise, all the angles that are located inside this circle and subtend on chord NP will be greater than 45 degrees. Like this angle, this is equal to 85 degrees in its size. Therefore, only the angles that are located on the circle itself, that is to say, their vertices are on the circle and subtend on chord NP, will be equal to 45 degrees in their sizes. Okay, so therefore, here we have, this is peripheral angle NQP that subtend on chord NP and is equal to 45 degrees in size. We know that if we rotate the vertex of this peripheral angle NQP along the circle without changing its size, we create infinite angles that each of them is equal to 45 degrees in size, and they all will be subtend on chord NP because we will not move the chord NP is the axis, we'll only move the vertex of the angle. We'll only move the vertex of the angle without changing the place of NP, that will be the axis. And we will not change the size of the angle. And therefore we create infinite angles that each of them will be equal to 45 degrees in its size, and are all subtend on chord NP. One of those angles will be angle PMN, that will be also equal to 45 degrees in size, and it's subtend on the same chord called NP. In this way, we created angle NMP. So in the next step, we'll join points M and Q together by side line. In this way, we created quadrilateral NMQP, that is definitely subtend is inscribed by this circle. Again, we created quadrilateral NMQP that is blocked by this circle or inscribed by this circle. So in conclusion, we found out that quadrilateral NMQP is a cyclic quadrilateral because it can be inscribed by this circle. So we can write down that quadrilateral NMQP is a cyclic quadrilateral, that is to say, it can be inscribed by circle. Quadrilateral MNQP is a cyclic quadrilateral. So we can block this quadrilateral NMQP by circle. So we'll block this quadrilateral NMQP by circle. The red circle blocks quadrilateral NMQP. Why the red circle blocks quadrilateral NMQP? Because of the fact that all of its four vertices, that is to say NMQ. Okay, so I made a mistake here. So this is the circle that blocks quadrilateral NMQP. Why the red circle blocks quadrilateral NMQP? Because of the fact that all of the four vertices of quadrilateral NMQP, that is to say point M, point M, point Q, and point P, they all lie on this red circle, and therefore the red circle blocks this quadrilateral NMQP. So we have the rule that states that the sum of the two opposite angles in a cyclic quadrilateral is equal to 180 degrees. Again, the sum of the two opposite angles in a cyclic quadrilateral is equal to 180 degrees. So the sum of those two opposite angles in quadrilateral NMQP must be equal to 180 degrees. So this is angle NPQ, that is the right angle, plus this is angle NMQ, the opposite angle NMQ. In product, the sum of those two opposite angles must be equal to 180 degrees, according to the rule that I presented to you. repeat again. In quadrilateral NMQP, the sum of the two opposite angles must be equal to 180 degrees because of the fact that quadrilateral NMQP is a cyclic quadrilateral. Angle, this is angle NPQ. That is equal to 90 degrees in its size. Plus this is angle NMQ. That is equal to 45 degrees plus x degrees in its size. In total, it must be equal to 180 degrees. So if we found out that 90 degrees plus 45 degrees plus the size of angle x, that is the angle that we are looking for in this question, in total it must be equal to 180 degrees. 90 degrees plus 45 degrees is 135 degrees. 135 degrees plus angle x, in total it must be equal to 180 degrees. Here we subtract 135 degrees from this equation, and when we get the missing angle x, that is the angle that we're looking for this question, is equal to 180 degrees minus 135 degrees is 45 degrees. So this is the missing angle x. That is actually also angle AMQ. Angle AMQ. That is also equal to x is equal to 45 degrees in its size. And that is the answer to the first question. In the next step, I present to you the second question, the answer on the second question of this lecture. In the second question, our task is to find out the area of this circle that is described by trapezoid ABCD. So first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. This is quadrilateral ABCD. In quadrilateral ABCD, side DC is parallel to the opposite side AB, and therefore quadrilateral ABCD is defined as a trapezoid because it has one pair of parallel sides. The two parallel sides, that is to say DC and AB, are defined as the bases of trapezoid ABCD. If we define the length of the base DC as A, that is to say DC equals to A in its length according to our definition, and we define the length of the base AB as B, then the area of this trapezoid ABCD will be equal to the sum of its two parallel bases, that is to say A plus B, times the height edge over 2. The height edge must create 90 degrees with the two parallel bases. So, repeat again, in conclusion, we found out that a trapezoid is a quadrilateral with one pair of parallel sides, and the area of any trapezoid equals to the sum of its two parallel bases. In this case, it is A plus B, times the height edge over 2. And the height edge must create 90 degrees with the two parallel bases. So, in the drawing, we have a circle that is described by this trapezoid ABCD. Those two angles are both right angles. We also know that side AB equals to 3 units in its length. And we also know that the area of this trapezoid ABCD is equal to 3 square units in its size. Equals to 3 square units in its size. Again, our task is to find out the area of this circle that is inscribed by trapezoid ABCD. So first of all, we'll define the relevant points to this question with letters. We'll define the center of this circle. This point is point O. Likewise, we'll define the point of tendency of tangent AB with this circle. This point is point E. We define the point of tendency of tangent DC with this circle. This point is point F. And finally, we define the point of tendency of tangent DC with this circle. This point is point G. In the next step, we will join points O and E together by straight line. We define the radius of this circle as x. Point O is the center of the circle, point E is the point of the circle itself, therefore OE is the radius of this circle. This is equals to x according to our definition. Here we can implement rule 1. I'll repeat quickly on rule 1. According to rule 1, a tangent to a circle is perpendicular. A tangent to a circle is perpendicular to the radius drawn to its point of tendency. In the drawing, we have a circle. We also have tangent AB that is tangent to this circle is point M. We also have the radius OM that is equals to R. The radius OM is drawn. The radius OM is equals to R. The radius OM is drawn to point M. That is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule 1. So we can implement rule 1 in our drawing. Why? Because in our drawing, we have the radius OE that is equals to x. The radius OE is drawn to point E, that is the point of tendency of tangent AB with this circle. And now you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius EO. If AB is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and F together by straight line. OF is of course the radius of this circle, is equals to x, and according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. I will not repeat on the same explanation. I will read it here. Likewise, we join points O and G together by straight line. OG is of course the radius of this circle, is equals to x. According to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. By doing all those constructions, we're going to do the small quadrangle DGOF. Inside this small quadrangle DGOF, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 pieces angle, in total it must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this 4 pieces angle must be equal to 90 degrees in its size. So quadrangle DGOF has 4 right angles, and according to rule 5, any quadrangle that has 4 right angles must be this rectangle if not a square. So we write to quadrangle DGOF as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So rectangle DGOF, side GO must be equal to the opposite side DF. But GO is x, therefore the opposite side DF must be also equal to x units in its line. Likewise, in the lower quadrangle FOEA, we have 1, 2, 3 rectangles, and therefore this 4 pieces again must be equal to 90 degrees in its size. So in quadrangle FOEA we have 4 rectangles, and therefore we can relate to quadrilateral FOEA is a rectangle. But we know that the opposite sides of a rectangle are equal to each other. So in rectangle FOEA, side OE must be equal to the opposite side FA. But OE is x, therefore the opposite side FA must be also equal to x units in its length. So in total, the length of side DA of trapezoid ABCD is equal to x plus x, that is 2x. So side DA of trapezoid ABCD is equal to 2x units in its length. In the next step, we'll define the length of side DC of trapezoid ABCD as A. It is given as a question that the length of side AB is 3. CB is the only missing side on trapezoid ABCD. We have already proved in the previous lecture that DA plus CB equals to DC plus AB according to rule 2. We have already proved that DA plus CB equals to DC plus AB according to rule 2. So we use it in our question. I'll not prove it again. DA plus AB equals to DC plus AB. It is true in any trapezoid, and also therefore it is true in trapezoid ABCD. DA plus CB equals to DC plus AB. According to rule 2. Again, we already proved that DA plus CB equals to DC plus AB according to rule 2. DA equals to 2x plus CB. CB is the missing side, so believe it is. And it is equals to DC. DC equals to A units in its length according to our definition, plus AB. AB equals to 3 units in its length according to what is given as a question. So in total, we actually found out that the 2x plus CB equals to A plus 3. Here, we subtract 2x from this equation, and we get that the missing side CB equals to A plus 3 minus 2x units in its length. So this is the missing side CB. This is the missing side CB. That is equal to A plus 3 minus 2x units in its length. In the next step, we will do a construction. That is to say, from this point C, we will draw perpendicular on AB. Again, from point C, we will draw perpendicular on AB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB. This point is point M. By doing this construction, you can deduct quadrilateral DCMA. So in the big quadrilateral DCMA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 450 degrees, total must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 450 angle must be equal to 90 degrees in its size. So inside quadrilateral DCMA we have 4 angles, according to rule 5, any quadrilateral that has 4 angles must be this rectangle if not a square, so let's for quadrilateral DCMA is a rectangle because it has 4 angles. But we know that the opposite sides of a rectangle are equal to each other. So in the big rectangle DCMA, side DA must be equal to the opposite side CM. But DA equals to 2x units in its length, and therefore the opposite side CM must be also equal to 2x units in its length. Likewise, according to the sum rule, in the sum rectangle DCMA, side DC must be equal to the opposite side AM. But DC equals to A, therefore the opposite side AM must be also equal to A units in its length. AM equals to A units in its length. What is the length of this missing line segment? Line segment MB. From the drawing it is very easy to see that MB equals to AB minus AM. AB minus AM equals to MB. So write it down. MB equals to AB minus AM. So MB in total equals to AB. AB is 3, according to what is given in the question. Minus AM. We just write down found that AM equals to A units in its length. So in total, MB equals to 3 minus A units in its length. MB equals to 3 minus A units in its length. In the next step, I'll copy the right triangle CMB in a new page, and we will implement the Badal's theorem on this right triangle CMB. According to the Badal's theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle CMB to the current from the original drawing. This right triangle CMB, CB squared, that is the square of the hypotenuse, equals to CM squared plus MB squared. So I write it down. CB squared, that is the square of the hypotenuse, equals to CM squared plus MB squared. CB equals to A plus 3 minus 2x, therefore CB squared will be equal to A plus 3 minus 2x squared. cm is 2x, therefore cm squared is 2x squared. 2x squared is 4x squared. Plus mb squared. mb is 3 minus a, therefore mb squared is 3 minus a squared. So in total we found out that a plus 3 minus 2x squared equals to 4x squared plus 3 minus a squared. Here we'll open the brackets on both sides of this equation. We'll do it according to the algebraic identity. We'll do it according to the algebraic identity that states that a minus b squared equals to a squared plus b squared minus 2 times a times b. Therefore, according to the algebraic identity that I mentioned, a plus 3 minus 2x squared will be equal to a plus 3 squared plus 2x squared. 2x squared is 4x squared minus 2 times a plus 3 times 2x, and it is equals to 4x squared plus 3 minus a squared. 3 minus a squared equals to 3 squared, that is 9, plus a squared minus 2 times 3 times a, that is minus 6a. We'll open the brackets of this expression. A plus 3 squared equals to a squared plus 3 squared, that is 9, plus 2 times a times 3, that is 6a, plus 4x squared minus 2 times a times 2x is minus 4x. So in total this expression equals to 4x times a plus 3. And it is equals to 4x squared plus 9 plus a squared minus 6a. So we have a squared on both sides of this equation, so a squared will get cancelled. We have 9 on both sides of this equation, so 9 also will get cancelled. And we have 4x squared on both sides of this equation, so 4x squared also will get cancelled. After we cancelled all those expressions, this side of the equation we left only with 6a minus 4x times a plus 3, while on the other side of the equation we left only with minus 6a. So in total we found out that 6a minus 4x times a plus 3 equals to minus 6a. Here we add 6a to this equation and also 4x times a plus 3 simultaneously, and we get that 6a plus 6a is 12a. So in this side of the equation we left only with 12a, while in this side of the equation we left only with 12a, while in this side of the equation we have 4x times a plus 3. Actually, in this side of the equation we left only with 4x times a plus 3, and in the other side of the equation we left only with 12a. So in total we found out that 12a equals to 4x times a plus 3. Here we divide this equation by 4, and we get that 12a over 4 is 3a equals to 4x over 4 is x, so in total this expression equals to x times a plus 3. So if we found out that 3a equals to x times a plus 3, here we divide this equation by a plus 3, and finally we get that x equals to 3a over a plus 3. And again, found out that x equals to 3a over a plus 3. In the next step, we'll calculate the area of this trapezoid ABCD according to the formula that I presented to you in the beginning of the lecture. So the area of trapezoid ABCD will be equal to the sum of its two parallel bases, that is to say it is DC plus AB, times the height, that is CM, because CM creates 90 degrees with the two parallel bases, so it is times the height CM over 2. And again, if we found out that the area of this trapezoid ABCD, in total it is equal to the sum of its two parallel bases, that is actually DC plus AB, times the height CM over 2. DC equals to A plus AB, AB equals to 3, according to what is given as the question, times the height CM, CM equals to 2x over 2. So in total, we found out that the area of trapezoid ABCD is equal to A plus 3 times 2x over 2. We have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. So we cancel 2, we left only with A plus 3 times x. So if we found out that the area of trapezoid ABCD in total it is equal to A plus 3 times x square units in its size. But it is given us in the question that the area of trapezoid ABCD equals to 3 square units in its size. So we can substitute the area of trapezoid ABCD by 3, and we get that 3 equals to A plus 3 times x. Repeat again. If we found out that 3 equals to A plus 3 times x. But we have already found out that x equals to 3A over A plus 3, so we can substitute x in this equation by 3A over A plus 3. If we do it now, we get that 3 equals to A plus 3 times x, and x is 3A over A plus 3. So in total, we found out that 3 equals to A plus 3 times 3A over A plus 3. We have 3A plus 3 in the numerator and A plus 3 in the denominator, so A plus 3 will get cancelled. So we cancel A plus 3. We left only with 3 equals to 3A. Here we divide this equation by 3, and we get that A equals to 3 over 3 is 1. So A equals to 1 unit in its length. Now we can substitute A in this equation by 1. We have the equation that states that x equals to 3A over A plus 3. And we have already found out that A equals to 1, and therefore we can substitute A in this equation by 1. And we get that A equals to 3A is 3 times 1, that is 3, over A plus 3. A plus 3 is 1 plus 3, that is 4. So in total we found out that x, that is the radius of this circle, is equal to 3/4 units in its length. Our task is to find out the area of this circle. Actually, we know that the area of any circle is equal to pi times the radius of the circle squared. Repeat again, the area of any circle equals to pi times the radius of the circle squared, and therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is x squared. So in total, the area of our circle is equal to pi x squared. So it is pi times x squared. X is 3/4, therefore x squared is 3/4 squared. 3/4 squared is 3 squared, that is 9, over 4 squared, that is 16. So in total, if you found out Then the area of this circle, this is the area that we're looking for in this question. It is equals to either 9 pi or 16 square units in size, or in terms of numbers, it is equals to 1.767 square units in size. Again, we shall find out that the area of this circle, that is the area that we are looking for in this question, it is equals to either 9 pi over 16 square units in size, or in terms of numbers, the area of this circle equals to 1.767 square units in size. So we finish with the second question. The next step, I'll summarize the next one. We'll start with the first question, of course. The first question, our task is to find out the size of this angle AMQ is equals to x. We have to find out the value of angle x. So in the domain, we have a semicircle. Point O is the center of this semicircle. AB is the diameter of this semicircle. In addition, we know that OA is equals to SB. Inside this semicircle, we have this square PQSO. Again, our task is to find out the size of this angle AMQ is equals to x. We have to find out the value of angle x. So first of all, we know that OPQS is a square, and all the angles inside any square are right angles. So those four angles are all right angles. In addition, we know that all the sides of any square are equal to each other. So in square PQSO, side QS equals to side SO. QS equals to SO. But it is given us the question that OS equals to SB. And from this equation, QS equals to OS equals to SB, we derive that QS equals to SB. QS equals to SB. In the next step, we need the construction, that is to say, we join points B and Q together by a straight line. Again, we join points B and Q together by a straight line. And we extended the straight line BQ by a straight line until it touches the circle. We define the touching point of the extended line segment BQ with this circle. This point is point N. By doing this construction, we can do that triangle QSB. But before that, we know that AB is the diameter of this semicircle. AB is the diameter, it is absolutely a straight line. So if you focus on the upper side of the straight line AB at point S, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. In this case, it means that the sum of the angles on the upper side of the straight line AB at point S must be equal to 180 degrees. So which angles we have at the upper side of AB at point S? We have this angle that is right angle, plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. So by doing this construction, we get the deal. The right triangle QSB. The right triangle QSB in front of those two equal sides, so we prove that QS equals to SB. So in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes, according to the rule that in front of equal sides in the triangle there are equal angles. So if the size of this angle is y, then the size of this angle must be also equal to y, because they are equal to each other according to the rule that I mentioned. So we know that the sum of the angles in any triangle is equal to 180 degrees. It is true in any triangle, and therefore it is true in triangle QSB. So the sum of the angles in triangle, the right triangle QSB must be equal to 180 degrees. So which angles we have in the right triangle QSB? Y plus 90 degrees. In total, they must be equal to 180 degrees. So in the right triangle QSB, the sum of the angles must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So 2y plus 90 degrees must be equal to 180 degrees. Here we subtract the 90 degrees from this equation, and finally found out that 2y equals to 180 degrees minus 90 degrees is 90 degrees. So 2y equals to 90 degrees. Here we divided this equation by 2, and finally found out that the missing angle y equals to 90 degrees over 2, that is 45 degrees. So actually, this is the missing angle y, that's equals to 45 degrees in its size, and this is also the missing angle y, that is equals to 45 degrees in its size. We joined points B and Q together by straight line. Then we extended the straight line BQ by straight line. When we extend the straight line by straight line, the result BN must be also a straight line. So if you focus on the left side of the straight line BN at point Q, here the sum of the angles must be equal to 180 degrees. According to all three, then the sum of the angles on one side of a straight line is equal to 180 degrees. In this case, it means that the sum of the angles of the left side of the straight line AB at point Q must be equal to 180 degrees. So which angles we have at the left side of the straight line AB at point Q? We have this angle that is equal to 45 degrees in size, plus this angle that is right angle, plus the missing angle NQP. In total, the sum of those two angles must be equal to 180 degrees according to all three. But again, we found out that the sum of the angles on the left side of the straight line BN at point Q must be equal to 180 degrees. That is to say, 45 degrees plus 90 degrees plus the size of the missing angle NQP, in total must be equal to 180 degrees according to all three. 45 degrees plus 90 degrees is 135 degrees. So 135 degrees plus the missing angle NQP, in total they must be equal to 180 degrees according to all three. So we have subtracted 135 degrees from this equation, and finally found out that the missing angle NQP equals to 180 degrees minus 135 degrees is 45 degrees. So this is the missing angle NQP, that is equals to 45 degrees in its size. In the next step, we join points M and N together by straight line, and we also join points N and A together by straight line. By joining points A and N together by straight line, we get the peripheral angle A and B. Peripheral angle A and B subtend on chord AB, that is the diameter of this semicircle, and according to rule 7, any peripheral angle that subtend on the diameter of the circle or semicircle must be equal to 90 degrees in its size. And therefore, peripheral angle in AP, peripheral angle A and B that subtend on the diameter of the semicircle must be equal to 90 degrees in its size. Okay. Now we have those two angles that are both subtend on chord AN. This is angle ANB, angle ABN, angle ABN subtend on chord AN. Likewise, this is angle AMN, angle AMN also subtend on the same chord called AN. And according to rule 16, if two or more peripherals subtend on the same chord, then they are equal to each other in their sizes. So those two peripherals that subtend on the same chord AN must be equal to each other in their sizes. But the size of this peripheral ABN is 45 degrees, and therefore the size of this peripheral AMN must be also equal to 45 degrees in its size. In the next step, I prove that quadrilateral NMQP is a cyclic quadrilateral. That is to say, it can be blocked by a circle. So first of all, what is the meaning of the sentence that a quadrilateral can be blocked by a circle? This is quadrilateral ABCD. Quadrilateral ABCD is blocked by this circle, or it is inscribed by this circle. Why quadrilateral ABCD is inscribed by this circle? Because of the fact that all of its four vertices, that is to say A, B, C, and D, they are all lie on the circle. And therefore, the red quadrilateral ABCD is inscribed by this circle, it is blocked by this circle. So we have to prove that quadrilateral NMQP is a cyclic quadrilateral. That is to say, we can block this quadrilateral NMQP by a circle. So first of all, I copied this angle NQP to a new page. This is angle NQP. That is also triangle NQP. The size of angle NQP equals to 45 degrees in its size. So copied triangle NQP in a new page. So actually, this is triangle NQP that I copied from the original drawing. Triangle NQP, angle NQP in triangle NQP equals to 45 degrees in its size. We have the rule that all the triangles in the world can be blocked by a circle. Therefore, triangle NQP can be blocked by a circle. So we block this triangle NQP by this circle. So in this way, we actually created peripheral NQP that subtend on chord NP. Again, we have peripheral NQP that subtend on chord NP. Peripheral angle NQP is equal to 45 degrees in its size, and it subtend on chord NP. But those two angles, they are both equal to 45 degrees in their sizes, and they are both subset on the same base NP. Again, those two angles are equal to each other, and they are both subset on the same base NP, and therefore those two angles can be blocked by a circle. They fit to be blocked by a circle. Here, this is peripheral angle PQN. This equals to 45 degrees in size, and it's subtend on chord NP. Likewise, this is peripheral angle PMN. This equals to 45 degrees in its size, and it's subtend on the same chord PN. So I copied those two peripheral angles in this page and blocked them by a circle. So in this way, I created two peripheral angles that each of them is equal to 45 degrees in its size, and it's subset on chord PN. It is very easy to see that any peripheral angle that subtend on chord NP and it is located outside this circle will be less than 45 degrees. For example, we have peripheral angle PLN. I measured the size of this peripheral angle PLN by scale. Actually, peripheral angle PLN that is located outside this circle is equal to 39 degrees in its size, that is less than 45 degrees. Likewise, all the angles that are located inside this circle and subtend on chord PN will be greater than 45 degrees, will be bigger than 45 degrees. For example, this is again PON, that's located inside this circle. The size of angle PON, that's subtend on the same chord PN, is 85 degrees, that is definitely greater than 45 degrees. In conclusion, you can say that all the angles that are inside this circle and subtend on chord PN will be greater than 45 degrees, while all the angles that are located outside this circle and subtend on chord PN will be less than 45 degrees. Therefore, we can conclude that only the angles that are located on this circle and subtend on chord PN will be equal to 45 degrees in their sizes. Those two angles are both equal to 45 degrees in their sizes, and the subtend on chord NP, and therefore each of them is equal to 45 degrees in size. So all the angles that subtend on PN and are equal to 45 degrees in their sizes must be on the circle itself, not outside the circle or not inside the circle. Therefore, we have this is peripheral angle PQN, this equals to 45 degrees in size, and it's subtend on chord PN. We can say that if we rotate this peripheral angle PQN around this circle without changing its size, and the base, the axis MP will not move, we create infinite angles that each of them will be equal to 45 degrees in size, and they are all subtend on chord NP. Why? Because we'll move only the vertex of the angle without moving its base, its axis. In this way, we get infinite angles that each of them will be equal to 45 degrees in its size, and they are all subtend on chord NP, because chord NP is not moving, only the vertex is moving. So out of the infinite angle that will be created by rotating angle NQP around this circle, out of the infinite angles that will be created, one of the angles will be angle NMP, that will be equal to 45 degrees in size, because we don't change the size of the angle when we move it, and it will be also subtend on chord NP, because chord NP is not moving. So in this way, actually created here peripheral angle NMP, peripheral angle NMP subtend on chord NP, and it is equals to 45 degrees in its size. So this is peripheral angle NMP that subtend on chord NP, and it is equals to 45 degrees in its size. So in the next step, we'll join points M and Q together by straight line. By doing all those constructions, we get the quadrangle NMQP, that is definitely inscribed by this circle. Or quadrangle NMQP can be blocked by this circle. So we should prove that quadrangle NMQP is a cyclic quadrangle. That is to say, it can be inscribed by circle, or it can be blocked by circle, because it is blocked by this circle. So in conclusion, we shall find out that quadrangle NMQP is a cyclic quadrangle. You can see also that all the four vertices of quadrangle NMQP, that is to say, vertex N, vertex P, vertex Q, and vertex M, they are all located on the circle itself. Therefore, quadrangle NMQP is indeed blocked by this circle, is inscribed by this circle. So we can write down that quadrangle NMQP is a cyclic quadrangle. Therefore, we can block this quadrangle NMQP by a circle. So I blocked this quadrangle NMQP by the red circle. You can see that all the four vertices N, M, Q, and P are located on the red circle. And therefore, quadrangle NMQP is blocked by this red circle. And we have the rule that the sum of the opposite angles of a cyclic quadrangle is equal to 180 degrees. That is to say, the sum of those two opposite angles in quadrilateral NMQP must be equal to 180 degrees. This is angle NPQ, that is the right angle. This is the opposite angle NMQ, equals to 45 degrees plus x. So angle NPQ, that is the right angle, plus the opposite angle NMQ, in total must be equal to 180 degrees. Repeat again that angle NPQ is the right angle, so I substituted angle NPQ by 90 degrees. This is angle NMQ, that is in total equals to 45 degrees plus x. So I substituted angle NMQ by 45 degrees plus x. So in total must be equal to 180 degrees. 90 degrees plus 45 degrees is 135 degrees. So 135 degrees plus the missing angle x, that is the angle that we are looking for this question. In total it must be equal to 180 degrees. Here we subtract 135 degrees from this equation and find out that the missing angle x is the missing angle, that is also equals to angle AMQ, is equal to 45 degrees inside. Again, the missing angle AMQ is equals to x is equal to 45 degrees inside. So we finish with the first question. In the next step, I present to you the second question, and we solve the second question of this lecture. In the second question, our task is to find out the area of this circle that is inscribed by trapezoid ABCD. Again, our task is to find out the area of this circle that is inscribed by this trapezoid ABCD. So first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. This is quadrilateral ABCD. In quadrilateral ABCD, side DC is parallel to the opposite side AB, and therefore quadrilateral ABCD is a trapezoid, because it has one pair of parallel sides. So in trapezoid ABCD, the two parallel sides, that is to say DC and AB, are defined as the bases of this trapezoid. So if you define the length of the base DC as A, and the length of the base AB as B, that is to say AB equals to B units in its length, according to our definition, then the area of this trapezoid ABCD, will be equal to the sum of its two parallel bases, that is to say A plus B, times the height edge over 2. The height edge must create 90 degrees with the two parallel bases. And again, in conclusion, we shall find out that a trapezoid is a quadrilateral with one pair of parallel sides, and the area of any trapezoid equals to the sum of its two parallel bases. In this case, it is A plus B times the height edge over 2. The height edge must create 90 degrees with the two parallel bases. So, in the drawing, we have a circle that is inscribed by trapezoid ABCD. In addition, we know that those two angles are both equal to 90 degrees. They are both right angles. We know also that this is side AB of trapezoid ABCD. This equals to 3 units in its length. And the area of this trapezoid ABCD is equals to 3 square units in its size, according to what is given as the question. Again, our task is to find out the area of this circle that is inscribed by trapezoid ABCD. So first of all, we defined the relevant points to this question with letters. We defined the center of this circle. This point is point O. Likewise, we defined the point of tendency of tangent DC with this circle. This point is point G. We defined the point of tendency of tangent DA with this circle. This point is point F. And finally, we defined the point of tendency of tangent AB with this circle. This point is point E. In addition, we define the radius of this circle as x. The radius of the circle equals to x according to our definition. In the next step, we join points O and D together by straight line. Repeat again, we join points O and E together by straight line. Repeat again. We join points O and E together by straight line. Point O is the center of the circle. Point E is the point on the circle itself. Therefore, OE is the radius of this circle. This is equals to x according to our definition. The radius OE, that is equal to x. The radius OE is drawn to point E. This is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius EO. If AB is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and F together by straight line. OF is of course the radius of this circle, it is equal to x. According to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. And finally, we join points O and G together by straight line. OG is of course the radius of this circle, this is equals to x. And according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in the upper quadrangle OGDF, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4-piece angle in total must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this 4-piece angle must be equal to 90 degrees in its size. So in quadrangle DCOF we have 4 right angles, and therefore we can relate to quadrangle DCOF as a rectangle, although that is actually a square. So a quadrangle in rectangle DCOF, the opposite sides are equal to each other. That is to say, side CGO must be equal to the opposite side DF. But GO equals to x, therefore the opposite side DF must be also equal to x units in its length. Likewise, in the lower quadrangle F4EA, we have 1, 2, 3 right angles. And therefore this 4-piece angle must be equal to 90 degrees in its size. And therefore can relate to quadrangle OFAE is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle F4EA, side OE must be equal to the opposite side FA. But OE is x, therefore the opposite side FA must be also equal to x units in its length. Side DA of trapezoid ABCD in total equals to x plus x, that is 2x. Again, side DA is definitely the straight line because of the fact that it is one side of trapezoid ABCD. Likewise, we define the length of tangent DC SA. We know that AB equals to 3 units in its length according to what is given in the equation, and CB is the only missing side in trapezoid ABCD. We have already proved in the previous lecture that DA plus CB equals to DC plus AB. And again, we have already proved that DA plus the opposite side CB in trapezoid ABCD equals to DC plus the opposite side AB according to rule 2. DA equals to 2x plus CB. CB is the missing side, so leave this it is. And it is equals to DC. DC equals to A according to our definition, plus AB. AB equals to 3 units in its length according to what is given as the question. So in total we should find out that 2x plus CB equals to A plus 3. Here we subtracted 2x from this equation and finally found out that the missing side CB equals to A plus 3 minus 2x units in its length. This is the missing side CB, is equals to A plus 3 minus 2x units in its length. In the next step, we did a construction, that is to say, from point C we do perpendicular on AB. Again, from point C we do perpendicular on AB. So actually this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB. This point is point M. By doing this construction, we get the quadrangle DCMA. The big quadrangle DCMA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4-piece angle in total must be equal to 360 degrees according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. and therefore this fourth missing angle must be equal to 90 degrees in its size. So instead quadrilateral DCMA, we have 4 right angles, and therefore can relate to quadrilateral DCMA is a rectangle according to rule 5. So quadrilateral DCMA is a rectangle, because it has 4 right angles. But we also know that the opposite sides of the rectangle are equal to each other. So in the big rectangle DCMA, side DA equals to the opposite side CM. But DA equals to 2x, therefore the opposite side CM must be also equal to 2x units in its length. Likewise, according to the sum rule, in the sum rectangle DCMA, side DC must be equal to the opposite side AM. But DC equals to A, therefore the opposite side AM must be also equal to A units in its length. What is the left of the missing side MB? From the drawing it is very easy to see that MB in total equals to AB minus AM. So MB equals to AB minus AM. MB equals to AB, that is 3, minus AM, that is 8. So in total AB equals to 3 minus A units in its length. In the next step, I copy the right triangle CMB in a new page and we implemented the Pythagoras theorem in this right triangle CMB. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right triangle CMB, that according to the original drawing. In the right triangle CMB, according to the Pythagoras theorem, CB square, that is the square of the hypotenuse, equals to CM square plus MB square. CB is A plus 3 minus 2x, therefore CB square is A plus 3 minus 2x squared. And it is equals to CM squared. CM is 2x, therefore CM squared is 2x squared. 2x squared is 4x squared plus MB squared. MB is 3 minus A, therefore MB squared is 3 minus A squared. So in total we found out that A plus 3 minus 2x squared equals to 4x squared plus 3 minus A squared. Here we open the brackets on both sides of the equation according to the algebraic identity that A minus B squared equals to A squared plus B squared minus 2 times A times B. So according to the algebraic identity that I mentioned, A plus 3 minus 2A squared must be equal to A plus 3 squared plus 2x squared, that is 4x squared, minus 2 times A plus 3 times 2x. And it is equals to 4x squared plus 3 minus A squared. 3 minus A squared equals to 3 squared, that is 9, plus A squared, minus 2 times 3 times A, that is minus 6A. We open the brackets of this expression also. A plus 3 squared equals to A squared, plus 3 squared, that is 9, plus 2 times A times 3, that is 6A, plus 4x squared, minus 2 times A times minus 2 times 2x times A plus 3, minus 2 times 2x is minus 4x. So in total this expression equals to minus 4x times A plus 3, and it is equals to 4x squared plus 9 plus A squared minus 6A. Here we have A squared on both sides of this equation, so A squared will get cancelled. We have 9 on both sides of this equation, so 9 also will get cancelled. And finally we have 4x squared on both sides of this equation, so 4x squared also will get cancelled. After we cancel all those expressions, in this side of the equation we're left only with 6A minus 4x times A plus 3, and on the other side of this equation we're left only with minus 6A. We added 6A and 4x squared times A plus 3 simultaneously to this equation, and finally we found out actually that 12A equals to 4x times A plus 3. Here we divided this equation by 4 and finally found out that 12A over 4 is 3A and 4x over 4 is x. So in total this expression equals to x times A plus 3. So in total we found out that 3A equals to x times A plus 3. Here we divided this equation by A plus 3 and finally found out that x equals to 3A over A plus 3. In the next step we calculated the area of this representative ABCD according to the formula that I presented to you in the beginning of the lecture. The area of this representative ABCD equals to the sum of its two parallel bases, that is to say DC plus AB, times the height CM over 2. With the area of the representative ABCD equals to the sum of its two parallel bases, that is actually DC plus AB, times the height CM over 2. DC is A, times AB is 3, and CM is 2x. Repeat again. DC is A, AB is 3 and CM is 2x divided by 2. A over, we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled, and we're left only with A plus 3 times x. So in total we found out that the area of trapezoid ABCD in total equals to A plus 3 times x. But it is given us the question that the area of this trapezoid ABCD equals to 3 square units in size. Therefore we can substitute the area of trapezoid ABCD by 3, and found out officially that 3 equals to A plus 3 times x. But we already found out that x equals to 3a over a plus 3, so we can substitute x in this equation by 3a over a plus 3. We did it, and in total we found out that 3 equals to a plus 3 times x. X is 3a over a plus 3. So in total we found out that 3 equals to a plus 3 over a plus 3 times 3 over a plus 3. We have a plus 3 in the numerator and a plus 3 in the denominator, so a plus 3 gets cancelled, and we left only with 3 equals to 3a. Here we divided the equation by 3 and found out that a equals to 3 over 3, that is 1. So a equals to 1 unit in its length. We have already found out that x equals to 3a over a plus 3. But we just right now found out that a equals to 1, so we can substitute a in this equation by 1. We did it, and we found out that x equals to 3a. 3a is 3 times 1, that is 3, over a plus 3. A plus 3 is 1 plus 3, that is 4. So in total we found out that the radius of the circle, x equals to 3/4 units in its length. Our test is to find out the area of this circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. And therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is x squared. So in total we found out that the area of our circle must be equal to pi x squared. X is 3/4, therefore x squared is 3/4 squared. 3/4 squared is 3 squared, that is 9, over 4 squared, that is 16. So in total we can find out that the area that we were looking for in this question, that is the area of this circle, equals to either 9 pi over 16 square units in size, or in terms of numbers, the area of this circle equals to 1.767 square units in size. Okay, thank you very much.